Okay, recording is now activated, so thank you everybody for showing up today. Highly, highly appreciated. Per the Vox Populi, which is Latin for according to the voice of the people, you all decided that we were going to meet on Zoom today to talk about infrared spectroscopy, which is good because otherwise we'd be in class just there and you would just be listening to me talk. So we can do that from the comfort of our own homes. I think either way is fine. So regardless, as I mentioned, this does not mean that this is not an important topic. This does show up on the final. You do have to keep studying for this. We are going to have a post-lab quiz in 2 weeks. And we are also going to have a Lab 4 worksheet from the course packet that you will have to turn in also in 2 weeks. So including this week and then the next week and the week after when it's due, there should be about 3 weeks total where you guys should be constantly studying this. And if you are going to take 223B, this will come back. This is just like TLC. You cannot do organic chemistry without understanding infrared spectroscopy. So make sure you're constantly reviewing, ask me questions about it, and we can get some good answers. All right. So, infrared spectroscopy. First, let's talk about spectroscopy. What does it mean? What is the word spectroscopy? Well, spectroscopy specifically is a technique where we shine photons of electromagnetic energy. The ones that we can see, we call that visible light. So everything that you see, if you look around, you're going to see colors, or even if you're colorblind, you will still see something. What you are seeing are the photons from the environment hitting your sensors in your eyeball, and your brain converts that into actual vision. So if you can see the visible light. And as you can see from this graph right here, visible light constitutes only a very, very small part of the total electromagnetic spectrum. And so you see we have visible light, we have infrared radiation, which has slightly lower energy than the color red, therefore we call it infrared. And usually we can't see infrared radiation, but we can feel it. If you've ever been around a campfire, if you've ever seen an explosion at Universal Studios or somewhere else, you can feel the heat. That is infrared photons hitting your body. But since we don't have the cells in our eyeballs to detect that, usually we just feel it as heat. And of course, we also have microwaves, which have an even longer wavelength. That's why we call them micrometer waves. We use that to heat up our food. We have radio waves, which I know you guys don't really listen to the radio anymore, but we use radio waves for Wi-Fi. So right now, if you're connected to a Wi-Fi source, you are using radio waves to transmit information. Next semester, you're going to learn about something called nuclear magnetic resonance that also uses radio waves. And the reason that we use radio waves for radio is because their wavelengths are very long and they can travel very, very long distances without losing intensity. And so we also have FM radio, which is more localized, and AM radio, which can go for hundreds and hundreds of miles. On the opposite side of the spectrum, where we have a lot more energy, more strong than even purple or violet, we have ultraviolet light. Ultra meaning beyond violet. So some lucky people have an extra cone cell in their eyes. I think it's a rod or a cone cell. I'm not sure which one. But some lucky people can actually see more colors and some part of ultraviolet light. I know birds can definitely see ultraviolet light. Bees can see ultraviolet light. They see it in the flowers. And if you've ever gone to raves or any sort of party where they have the UV lights, you can see what happens when UV light hits a material that absorbs it and re-emits it in something that is visible. That's why we have the highlighter colors. If you've ever gone to the dentist or you're planning to become a dentist or a doctor, you will most likely be using X-rays, which are very, very high energy, dangerous photons of electromagnetic energy. And I'm sure you guys have taken X-rays, so you can see that it's so high energy that it can actually go through the skin and partially through the bone, which is why we're able to see the structure of our bones, right? So the guy who discovered X-rays, he first took a picture of his wife's hand with her ring on, and when he showed it to her, she says, "Oh my God, I have seen my death." You can read out the whole story all about that, but yeah, it was discovered by a German dude named William Roentgen or Röntgen. I'm not exactly sure how to pronounce it, but fairly recent. It hasn't even been about 150 years. But X-rays are very high energy light. That's why the dentist or the doctor goes and presses a button from very, very far away. And that's why you have to wear the lead blanket because it's going to protect you. And they only really expose it for a few seconds at most. You don't really want to be exposed to X-rays. Even more energetic than X-rays, we have gamma rays, which is, I believe, what turns Superman strong in the movies and in the comics, right? Like his planet usually has higher amount of gamma rays that are hitting him. So when he comes to Earth, I mean, relatively speaking, I don't know if he gets more or less, but he uses that to gain his powers. And you always have even more energetic rays. At that point, you're talking about black holes, you're talking about reality breaking photons. We don't really we get bombarded by cosmic rays every day, but we get a pretty good shield from the magnetic field from the planet. But in short, this is the entirety of the electromagnetic radiation spectrum. And all of this is carried by photons. The photon is the carrier particle of the electromagnetic radiation. And the only part that we can see are a very, very, very narrow portion of it that we call visible light. Usually it's 400 nanometers to 700 nanometers. This light goes 400 to 800 nanometers. We can measure wavelength in meters. That's the standard unit. We can measure it in micrometers. We can measure it in nanometers. It really depends on the scope that you're talking. So does this make sense so far? Any questions about the electromagnetic spectrum? Or I mean, I'm sure this is not the first time you've heard or seen this, right? If you've ever seen a rainbow in the sky, you can actually see all of the colors that we can see with our eyeballs scattered on the sky. And these are governed by some physical equations. You can see here we have the speed of light c, which is a constant. That can be derived by multiplying the wavelength times the frequency. We have energy, which is a Planck's constant h times the frequency. And you can simply define the frequency as the speed of light divided by lambda, which comes from this first equation over here at the bottom on the left. So, I mean, you're not expected to necessarily know the equations, but this is supposed to be something you should have seen once or twice, and you should know at least the relationships between them. So if you have any questions about that, definitely let me know. This is just primer. This is the foundational information before we get into the little details of infrared spectroscopy. But in short, for spectroscopy, we take a source of photons, and it could be UV, it could be infrared, it could be radio waves, it could be X-rays. We use all sorts of energies in science. And we shine it at a piece of matter, and the piece of matter interacts with it somehow. And then it re-emits it either in the same region or in a different region, and then we measure it. And that measurement, we can graph it, and it can give us information about the compound. So in this case, we're going to be using infrared radiation, and we're going to be using it to tell us about the functional groups of organic molecules. So any questions so far before I continue? If at any time you have a question, let me know in the chat. Alrighty. So, as I mentioned already, different types of wavelengths are used for different purposes. In this case, I just want to focus on the IR spectroscopy, the infrared spectroscopy. As I mentioned, this is going to give us information about functional groups in organic molecules. Now, in organic molecules, I'm sure you have started to talk about, or at least are somewhat more familiar in your lecture about what functional groups are. They are the parts of the molecule that react. So when you have a molecule that has a bunch of carbon hydrogen chains, and you have a chemical reaction, the entire molecule does not always react. Sometimes only one part of the molecule is going to be reacting. And we call that part, it could be composed of carbon and oxygen, or carbon and chlorine, carbon and fluorine. It could be a double bonded carbon. It could be a triple bonded carbon. It really depends on the molecule you're using. But we call these pieces functional groups because they function in the chemical reaction. And the infrared spectroscopy is used so that we can analyze the molecule over a range of energies. And depending on what functional groups are present in that molecule, that is going to tell us and give us an idea as to what molecule we have. Because, I mean, think about it. Molecules are tiny. We can't see them, right? How do we know what they actually are? How do we determine if something is a carboxylic acid, or if something is a ketone, or if something is an ester? How do we confirm it, right? We could just be making it up. And the way we do it is we use spectroscopy. There are people who dedicate their entire lives to studying spectroscopy. So if you want to make a career out of it and you get really good at it, you can make some decent money and you will be invaluable for sure. And AI definitely cannot do spectroscopy very well at all. So this is a skill that is definitely worth developing if this is something that's interesting to you. All righty. So how exactly does the absorption work? Well, you might remember from Chem 111A that you have these things called energy levels, right? We have n equals 1, n equals 2, n equals 3, all the way to infinity. And between these two energy levels, we call one the lower energy, or the ground state, right? So if you think about it, you are always in a ground state because you're actually on the ground. If somebody wants to take you to the next energy state, you have to actually be lifted up, or you have to take something that lifts you, right? So if, for example, here in the library on the fifth floor is clearly n equals 5 compared to n equals 1. So what does that mean? It means that in order for you to go from n equals 1 to n equals 5, there has to be an amount of energy that you put in to take you from n equals 1 to n equals 5. And that energy, you can feel it in the elevator when it's lifting you up, right? So the same thing happens inside atoms and molecules. They all have different states of energy, with the most stable, the most naturally occurring one being called the ground state. And they can all be excited. This is the words that we use. They can get excited to the next energy level. But in order to do that, you have to put energy into the system, and it has to be an exact amount of energy, right? There is no floor 1.5. There is no platform 9 3/4 like there is in Harry Potter. There's only n equals 1, n equals 2, n equals 3. There's only whole integer multiples, right? And so you need an exact amount of energy in order to move an electron from the n equals 0 state to the n equals 1, or to the n equals 2, or to the n equals 3, and so forth and so forth. There cannot be any in between states. And so the electron absorbs that photon, uses the energy to jump to the next energy level. It stays there for a little bit, and then when it comes back down, it releases that energy. And that energy can be released as a photon. And that is what our eyes perceive as color. So all the colors, right? All of the blues, all of the greens, all of the reds, every color that you see is the result of light interacting with matter. The matter absorbs the photon, and then the photon goes back down to the regular energy level, and the energy that it re-emits goes to your eyeball, and that is a color. That is what we see as color. And carrots are orange because when it absorbs that electron and it comes back down, the energy level matches the energy of the color orange. And paint is white because it absorbs all the colors, because it has different energy levels, and it scatters everything, and we just see that as a simple white color. So this is a lot more physics oriented if you're really curious. But in short, what you need to understand as part of the fundamentals is that the reason this works is because matter can absorb photons, and then those photons can be re-emitted either as visible light, which is what we can see, or as ultraviolet light, or as X-rays. The X-rays are generated by copper, or as infrared radiation. So any questions about this? So this is basically what I said, right? Depending on the type of energy that you have, you get different types of absorption and re-emission. So again, this is mostly physics. You don't really need to know the actual physics or the physical equations, but you do need to understand the process, right? From what I've seen on the final exam, you mostly get asked about relationships, like what is the relationship between energy and frequency, or what is the relationship between energy and wavelength, right? So you don't necessarily have to do physical equations, but you should understand what they mean or what the relationship between the two is. So any questions before I move on? And again, at any point, just go ahead and ask me questions on the chat. I'll be more than glad to answer them. Alrighty, so here we go. Infrared spectroscopy specifically. So again, we have the electromagnetic spectrum. We focus only on infrared, which has lower energy wavelengths than red. So we call it infrared. Infra is a Latin word meaning below. And then that gets absorbed by the molecule. And it just so happens, this is just how nature works, how it was designed, how it evolved, whatever you want to call it. It just so happens that the energy for a bond to vibrate like an accordion, or if you work with cars, you know about the springs, the shocks, right? They absorb energy, and that's why every time you drive on the freeway, you're not constantly feeling the bumps because your springs absorb that energy. We could think of bonds like springs. And even though in class, every time we use the modeling stuff, we always see that the bonds are simply static. That's not how it actually works. In the real world, bonds are flexible to an extent, and they can vibrate. So one of your pre-lab quiz questions was, what kind of motion does infrared spectroscopy measure? The answer is vibrational motion. Infrared spectroscopy measures the vibrations of the bonds. And you might remember from 111A and 111B that single bonds are weaker than double bonds. Double bonds are weaker than triple bonds. And then polar bonds are also strong because of the polarity difference. And also metallic bonds are even stronger. And then we also have ionic bonding and covalent bonding. So depending on the type of bonding that you have, depending on the strength of that bond, you're going to have different energies that correspond to the vibration of that spring, right? Think about your car. Your car weighs about 2,000 to 5,000 pounds. If you go and sit in your car, ideally, you should not feel your car going all the way to the floor, right? But then if like six people in your family get in the car, you'll definitely feel your car go lower. Well, that's because it takes energy to vibrate those springs. And in this case, the reason we're using infrared for spectroscopy is that the energy required to vibrate those bonds happens to match the infrared spectrum of energy. So if you've ever taken physics, you might have heard something called the harmonic oscillator. That's just a fancy way of saying spring, because if you've ever had that experiment where you have a spring and you put a mass at the bottom and you simply pull the spring is going to bounce up and down, and we can calculate the strength of the spring. And then also depending on the mass that is located on that spring, and then also depending on the amount of energy that you pull the spring, you can graph it and you will see a wave function, and then that can be used to determine what kind of stuff is on that spring. Is it a heavy mass? And that mass can be considered a heavy atom. Or is it a light mass? Can you have two springs connected in parallel? So forth and so forth, right? Again, this is a lot of physics, but I'm sure you guys have played with springs inside your pens, inside your cars, maybe some toys. If you've ever played with a slinky, that is a very weak spring that you can simply, go back and forth. Yeah, this used to mean something else back in the day. So yeah, so this is basically the model that we're using to explain infrared spectroscopy. And if you really, really, really care, you can take physical chemistry, which is an upper division class, and you can actually calculate how many vibrations a molecule will have and what their energy is going to be. And we'll get to that. But before we do that, again, any questions before we proceed? Alrighty. So this is the instrument that we use. It's actually in that hallway where we do the TLC UV visualization. Very small instrument. We've done a good job at refining it and making it portable, mobile. What you do is you take your compound and you put it right here. I'm going to use the color orange. It's a very, very small amount. It used to be that you had to prepare a whole thing for it, but now you can just put it directly on there and you can bring the sensor down and it'll shine some infrared photons through it, and then we take a spectrum. You can see down here, we have on the y-axis, we have something called percent transmission from 100 at the top to 0 at the bottom. And then on the x-axis, we have something called wave number. And wave number, this is the formula for wave number over here. It's the inverse of the wave length. Why did they decide to do it this way? I don't know. Look up the history of chemistry. I am noticing a trend nowadays where they are starting to just use like absorption, so the spectra can be backwards instead of transmission. But regardless, the information is all the same. And notice as well that the wave number is listed in inverse centimeters. Look at the units right here. Centimeters to the -1. And that -1 tells you that it's at the bottom. So that's how we know that it is the inverse, right? So if you want to use your energy formula, energy is equal to Planck's constant times the frequency. Well, if you want to use the wave number, like organic chemistry scientists use it, you can simply do a substitution and you can get your formula right there. Again, you don't necessarily have to know this, but you do need to understand the relationship. That might show up on the final for sure. And so the wave number is directly proportional to the energy. You can see this bullet point right here. It's directly proportional to the energy. What does that mean? It means that if you have a high wave number, as your wave number goes up, your energy also goes up. So if you look down here at this graph on the bottom right, you'll see that the x-axis on the very right, it's 400. This is low energy. So right here, it has low wave number. So we say that this is low energy. And then if you look on the very left, it goes all the way to 4,000. It's not linear, it's a logarithmic graph. This 4,000 is a high wave number, and therefore it has a high energy. Okay. Directly proportional. If one doubles, the other one doubles. If one triples, the other one triples. It is a direct correlation. And this is only true with wave number. Wavelength is inverse. Okay, so one of the questions you might see will be, what is the relationship between energy and wave number? Direct, directly proportional. What is the relationship between energy and wavelength? Inverse, right? If one goes up, the other one goes down. You do have to know at least this foundation, right? Because it is going to help you. But what we're going to be doing for the worksheet is I'm going to be giving you guys these spectrum, and you're going to have to look at the energies where you see these peaks. And then based on that, you're going to say, well, this really long peak here has a wave number of 3,200. This sharp peak at 1,500. This sharp peak at 1,000, right? 1,000 wave numbers, 4,000 wave numbers, 400 wave numbers. That is how we talk. And this is the graph that you're going to be seeing on the final. This is the graph you're going to be seeing in the post-lab quiz, et cetera, et cetera. You need to understand what wave number is and how it relates to the energy of that functional group. All right. And yes, this is a standard spectrum. Usually we measure from 400 to 4,000. And you will see here that some peaks are very strong peaks. Some peaks are very sharp. Some peaks are broad. Some peaks are weak. Some peaks are not, I don't know what's the opposite of sharp, like blunt, soft. I don't really know, right? We do have a language to describe it, but right now I just want you guys to understand this relationship between wave number and energy. So any questions so far about anything? All righty. Again, ask me anytime. More than glad to answer. So let's see. How do I clear my annotations? There we go. And then I can go back to regular and then I can click next. Okay, cool. Oh, yeah. See, that's what I was asking. How do I clear the drawings? There we go. Alrighty. So again, just one more time, I just want to emphasize that the logic behind this is just a spring model. You can think of this green sphere as oxygen, for example, and this other green sphere as another oxygen. So you have a spring, you have two masses between them, and then it takes a certain amount of energy to vibrate that spring like an accordion. Or maybe you don't have the same atom. Maybe on one side you have a hydrogen, and on the other side you have a carbon. So now you have a carbon-hydrogen bond which vibrates at a specific frequency. Or maybe you have a carbon-carbon bond, and then you can plug in your mass. We know carbon has a molar mass of 12 grams per mole, and we can calculate the energy of that frequency. Or maybe you have a double bond. So now you have a carbon-carbon double bond, and you can see how much energy it would take to vibrate it. And so forth, right? There's a whole physics equation here. If you're more math oriented, you can see here we have all these constants. But the important part is the reduced mass, right? We have to take the masses of the two atoms and reduce it so we can find the center of mass. And then we can plug that into this equation. We have the force constant, which is simply the strength of your bond, right? How strong is your bond? And then we're able to calculate or predict the general wave number. And so we have, what's called the low vibrational energy state, where there's hardly any vibrations. The bond is kind of just standing still, not really doing much, right? The low vibes. And then you have the high energy vibrational state where the bond is just going crazy and it's vibrating like crazy. And yes, if you have a high enough energy, the bond actually breaks. You can break a spring, right? If you have enough strength to pull it apart. You can also break a bond if you have a high enough energy going into it. And that happens mostly in space, where the cosmic rays are so strong that they actually break the bonds and you just have free atoms roaming around. And that's why space is dangerous, right? It can literally take the atoms out of your body and just reduce you to dust. So, yeah. And then we remember from 111A and 111B that, again, a single bond is weaker than a double bond. A double bond is weaker than a triple bond. So the strongest bond would be triple, double, single. And then we also have bonds that have like a really heavy atom, for example, bromine and hydrogen. Well, hydrogen weighs only one. Bromine weighs, I believe, 78 or 79. You can look it up on your periodic table. And instead of being an even spring, it's going to be more like a paddle ball, where one of them kind of stays in place and the ball is just kind of going around all over the place. That's going to have a high vibrational energy state. So it really does depend on the mass of the atoms. It depends on what type of bond you have. And of course, it also depends on the polarity. So we'll talk about that as well. So any questions? This is simply just physical overview. You don't have to know the reduced, the Hooke's law reduced mass harmonic oscillator formula, but you do have to understand what factors affect the wave number. So any questions? So the x-axis that you saw on this chart earlier, let me go back real quick. The x-axis, the wave number, that has to do with bond strength. So you can write that down in a sentence. The x-axis tells you the bond strength. So what does the y-axis tell you? The y-axis tells you the bond polarity change. The more the polarity, the dipole changes in the bond, the stronger the signal is going to be. So you're going to see that this peak is going to drop very close to zero if the bond has a high dipole change. And you have to be careful because this is where a lot of people get confused. Some people are saying, well, you told me polar bonds are strong bonds. Yeah, polar bonds in general tend to be strong bonds, but we're not measuring the strength of the polar bonds. Yes, we are. That is the x-axis. But we're also measuring the vibration of that polar bond. If a bond is polar, it should already be strong, right? But a single polar bond is going to still be weaker than a double polar bond. What matters is how intensely does that bond vibrate? And if when that bond vibrates, is there a change in polarity? And if the change in polarity is big, you're going to see the intensity be very close to the bottom. So we'll explain. We'll explain. Again, I don't expect you guys to just learn everything right away from one lecture, especially on Zoom, but we will explain this, right? But for now, what you can write for sure is your x-axis is going to determine your bond strength, okay? And remember, the higher the wave number, the higher the energy. So high wave number means strong bond. Low wave number means weak bonds. Okay? Any questions so far? Yes, I have a question on the chat. So wavelength and energy are inverse, but wave number and energy are proportional. Correct. That is correct. Yes. Good question. All righty. All right, moving on to the next slide. So again, why do we use IR? Why don't we just use X-rays? We actually do. I took a whole class last semester called X-ray crystallography, and we shoot X-rays at atoms, and we can actually determine the distance between them. But that took a lot of math, and it was very intense. So if you're interested, go to grad school or take X-ray crystallography in upper division. Why don't we use visible light, right? We do. We call that UV-vis spectroscopy. You have a UV-vis spectrometer right now in your body. We call them eyeballs. So you can. Generally, red has lower energy than orange, right? We have the rainbow, Roy G. Vib. Purple and violet have the highest energy. Red and orange have the lowest energy. So you can actually tell just with your eyeballs if something in front of you, like a red pen, is made out of molecules that have lower energy bonds compared to something that is blue, which has something that has higher energy bonds. But I mean, color is one thing we can use, right? It doesn't really tell us much more. We use IR specifically because when we're trying to figure out what functional groups a molecule has, again, just by coincidence, the strength of those bonds happens to match the infrared spectrometry spectrum. And that's really why we do it, just because it happens to match, right? If it had been visible light, we would be using visible light. And some do. And that's also why we use UV-vis spectroscopy. We also do NMR, but NMR tells you more about the specific spin of the hydrogen atom. So you guys will learn all about that next semester. There's no need to get into it. But again, we use IR specifically because that tells us the vibrations of the functional groups in the molecule, and it gives us a hint as to how we can identify the molecule, right? So far, we've used TLC. So far, we've used column chromatography. Well, now we can use direct methods to directly conclude what atoms are present in the molecule. That is the cool thing about IR. And you got to be careful because remember, IR depends on a change in the dipole, right? The polarity has to change when the bond is vibrating. If the bond vibrates, but there is no change in polarity, so for example, we learn about the diatomics in 111A and 111B. We have H2, N2, O2, F2, Br2, I2. Well, think about it. You have hydrogen and hydrogen. And if you vibrate them, well, there is no polarity difference. So there's not going to be any IR measurable bands. And same thing with nitrogen. If you have nitrogen and you vibrate them, even though the bond is vibrating, there is no change in polarity. So you cannot see it on an IR spectrum. And you might have something like a carbon molecule. sorry, carbon dioxide, where you have carbon and two oxygens on opposite sides of each other. Well, if you're vibrating them at the same time symmetrically, even though you have a polar bond, the fact that they are both canceling each other out and vibrating at the same time means that overall the polarity doesn't change, and therefore you are not going to see that on an IR spectrum. So you have to be very careful. Most functional groups are visible in an IR spectrum, but not all of them. Only the ones that have a change in the dipole can be observed. All right. There is a way to see them. We measure the rotation. We call that Raman spectroscopy, which is very similar, but we don't talk about that here. That's an upper division topic. And so again, if you see down here in the blue, you can see exactly what I just told you. The greater the change in the dipole moment, the more intense the absorption. And if there is no change in dipole, you cannot see it in an IR. We can only see the bonds that change when they vibrate, that polarity changes when they vibrate. So if you remember, oxygen is more electronegative than nitrogen. So that one is going to have a higher energy, higher wave number. And also when you see it on the y-axis, the peak is going to be closer to the bottom because it's going to be very intense. That is the word that we use, intensity. So your y-axis is your bond dipole change intensity. X-axis is the bond strength. Y-axis is dipole change intensity. Okay, they are not exactly the same thing. And so you can see oxygen, because it's more electronegative, will have a bigger dipole change than nitrogen. Nitrogen is more electronegative than carbon, so it's going to have a more intense peak than carbon hydrogen. So any questions so far?
Can you repeat the y-axis?
I couldn't really hear you. I'm sorry. You asked me to repeat something, but I wasn't sure what you asked me to repeat. Can you repeat the y-axis? Yes, I can. The y-axis measures the bond dipole change intensity. Bond dipole change intensity. So for example, you can see here we say OH, right? We have oxygen on one end of the spring and we have hydrogen on the other end. Oxygen is more electronegative. Let me see if I can draw this out. Hold on. I tried to use my tablet today, but I couldn't, so it's gonna be a little difficult for me. So I'm just gonna draw the dipole arrow right here. Right? Oxygen is more electronegative, so the dipole points towards a more electronegative element, oxygen. And if we vibrate that OH bond, well, there's already a polar bond. And then when you're vibrating it, you're changing it, right? When you bring it far away, the polarity decreases because it's based on distance. And when you bring it closer together, you get an increased polarity. So your polarity is going, large and small, large and small, large and small. So if you plug that into your y-axis, let me go back to the chart so you can see it. If you plug that in, you're going to see that OH actually right here. You can see this whole peak. This actually is an OH vibration peak, OH. And you can see how the y-axis is very close to the bottom, right? It goes from 0 to 100. Well, it also measures downwards, right? So this is a very intense peak. You can see the peak is large. That's what we mean by intense. It almost touches the ground. That's very intense. Why is it so intense compared to, for example, this one right here? You see how these are barely, I mean, they're very weak peaks. You can see they're very small. Why is one bigger than the other? Because the OH has a bigger change in polarity compared to something like CH. Like these ones that I circled over here, these are CH bonds right here. Very weak. Carbon and hydrogen don't have a lot of electronegativity difference. So there's not a lot of change. So even though you can see the wave numbers on the x-axis, the strength of the bond, you see the polarity change on the y-axis. So your y-axis is your polarity change intensity. That make sense?
So the smaller the the dip,
Yes,
the smaller the polarity change between them.
exactly. Yes, exactly. Yeah.
Separate.
Yes, exactly.
Okay.
Yeah.
All right.
Yeah. Good question. Good question. Yeah. And again, I don't expect you guys to just walk away from today's lecture and be like, I know IR, right? Like in the Matrix, like, I know IR, show me. No, you got to keep studying this, right? You got to keep studying this. Like, people make whole careers out of studying this. So it's not something that you get on the first day, right? What we're trying to help you identify is if you look at this spectrum here, based on the information I'm giving you, just like I just showed you, you should be able to tell me this is an OH peak. This is a CH peak. This is a carbon double bond oxygen peak. And if you put all that together, you can tell me what's in your molecule, right? So I'm just trying to make you make sense of these squiggly lines, right? It looks like a whole bunch of nonsense right now, but based on these principles, by the time we're done with today's lecture, you should be able to tell me, oh yeah, that's definitely an OH. Oh yeah, that's definitely a carbon double bond oxygen, so forth and so forth. So that's what we're trying to get you to do. We don't want you guys to be complete experts on IR. We want you to take a look at a graph and say, this is not squiggly lines. This is real information that can tell me real stuff. That is the goal for today. So yeah, good questions. All right, so we were right here. Okay, so any more questions before I continue? All righty. Okay, so moving on to the next slide. So how exactly do these bonds vibrate, right? So we've been talking about how bonds can vibrate. But remember, a molecule is multiple bonds in a structure. We don't just measure one specific bond. We have a whole molecule. It could be a small molecule like methane. It could be a large molecule like dodecane. It could be a whole plastic, right? Plastic molecules have chains of thousands of repeating carbons. That's why they're all flexible and moldable and stuff. So how exactly do these molecules move? This is where I'm going to take a small pause from this presentation, and I'm going to share my screen and show you a really cool website that I want you guys to take a look at when you get the chance. So give me a quick second. I'm going to stop sharing my screen, and I'm going to switch to my browser, and I'm going to show you a cool website. So let me see. All right. Okay, so here we go. This is a really cool website. If you're going to stay in chemistry or you're going to do biochemistry or anything related, and you're going to take upper division classes, this is going to be a cool website for you to look at, especially if you're a visual learner like me. You can actually see a model of the molecule. So everybody can see the water molecule, right? Nope, no problem. Everybody can see what's on my screen. This website is called CHEM223A.com. And if you go to structure and bonding and you click where it says molecular vibrations IR, you can see some example molecules. So you can get an idea of how these molecules vibrate. Remember, we cannot see molecules. They're way too small. We are not Ant-Man, and we cannot shrink down to the quantum realm to actually see what atoms look like. We have to deduce based on what we can observe. So everybody knows water, right? I hope you drank water today. And if you don't, now's your sign to do so. So here's water. We know that it is sp3 hybridized. The angle is 109.5. How does this vibrate? Well, right here, you can see there's a menu, a drop-down menu, and it says 3 vibrations, 1711, 3730, and 3851. And notice the units. These are inverse centimeters. So these are what? Starts with a W. What are these numbers? They are what? What? Wave what? Somebody type it or say it. These numbers here, they measure something. What is it? Wave what? Oh, we got a chat. Wave numbers. That's right. These are wave numbers. How do we know they are wave numbers? Because the units are centimeters to the -1. Okay. So there's 3 vibrations that a water molecule can have. Let's go ahead and click on the first one. Look at that. So we call that a symmetric bending. Right here, you can see bend wave number 2. And so it's kind of like a yoga stretch. Like if I have my 2 hydrogens and my head is the oxygen, you can kind of see that it goes like this, right? It goes like this. And this is actually how it moves, right? This is an actual vibration mode of water. So you can do a workout like this. And then you can see the number. This vibrates at 1711.15 wave numbers, right? 1711. And so remember, our spectrum goes from 400 to 4,000. This is at 1711. So it's kind of on the weaker side. Let's take a look at the other ones. Look, the wave number jumps up to 3730. So this one is a much higher energy vibrational state. Let's check it out. Look at that. So we call that one the symmetric stretch, this one here on the top right. And that one is kind of like, again, if you want to use your hands and you want to think of your hands as the hydrogen molecules and your head as the oxygen molecule, you're doing a symmetric inside and outside kind of motion like this, right? So we call that the symmetric stretch. Notice we have 2 types of vibration so far. We have bending, where you're actually bending your arms, and you have the stretching, where you're actually going inside and outside of the molecule, right? And this is called the symmetric stretch. And if we look at the final one, you see we also have another stretch, but in this one of the hydrogens is close to the oxygen and the other one is far away. And then it goes back and forth like this, right? It goes back and forth like this. And again, this is real. This is actually measurable. This is actually calculatable, computable. This is something that you can determine from theory, and this is something that you can observe when you actually put water in an IR spectrometer. So water has three modes of vibration. That's how we talk about it. And we have a symmetric stretch, an anti-symmetric or asymmetric stretch, and we have a symmetric bend. And so if you take an IR spectrum of water, you will see these peaks at these wave numbers that correspond to these vibrations, stretching, or bending. And, future business idea, you can open up a chemistry Pilates class that is based off of the movements of the molecules, right? You can say, move like molecules do, man. Yeah, yeah. It actually is true. The molecules are vibrating, man. The hippies were right all along. So does this make sense? Are you guys kind of seeing what we're talking about when we talk about vibrations? Any questions? So let's try another one just for the fun of it. Let's see. We have carbon dioxide. And let me see, I think it should be loading. Let's see, IR, carbon dioxide. It's taking some time to load. Let me see if I can get another one. Let's look at methane. We know methane. Okay. Yep, of course, it's not showing up now. Let's do one more. If this one doesn't work, then you guys are gonna have to check it out on your own. I really want to show you methane though. Methane is cool. Let me try stopping the share and starting the share one more time. Hold on. Refresh. Yep, it doesn't seem to be working this time. Alrighty. Any more? Any more that can work? Yep, website seems to be acting up. Well, anyway, I hope you guys understand the purpose of what I was trying to illustrate with this, right? Good thing the water example actually worked. What I'm trying to emphasize is that molecules vibrate, man. They really do vibrate, and they vibrate in a very specific motion. So again, if we go back to the slides now, you can hopefully these pictures make a little bit more sense now that you've actually seen them move, right? You can see the bonds can go in and out towards the center of the molecule, or one can go out and one can stay in, or they can both bend together, or sometimes they bend towards each other like this. Like if you're doing those, haven't gone to the gym in a while, so I don't really know what you call those hugging, motions. And you can also do the ones that work out on your back, right? So the molecules are vibrating in all sorts of different ways, and we can observe the wave numbers of those vibrations in our IR spectra. All right. And again, the wave number corresponds to the energy of those vibrations. Higher energy wave numbers have higher numbers, right? Big number, big energy. Small number, small energy, right? Big wave number energy. All right. And again, depending on some molecules, like I was trying to show you carbon dioxide, you can see carbon dioxide does have strong polar bonds, but if you have a symmetric stretch where they're both changing the dipole in opposite directions at the same time, that is going to be IR inactive. It is not going to show up in your IR spectrum. Okay? But if you have something asymmetric where there is some sort of change, one is changing while the other one is not, that vibration will show up on the spectra. So this is something you do have to keep in mind. I took an entire class in upper division of symmetry. I never thought I would take a class on symmetry. I thought it was chemistry, but a lot of chemistry is actually based on the symmetry of the molecule. It's really cool stuff. And again, it makes you realize the hippies were correct. So this is the principles of IR spectroscopy. This is what we use as our foundation so that when we are analyzing our spectra, we know exactly what we're looking for. So any questions about anything so far? All righty. Again, questions at any time, let me know. So now we get to the actual core of today's lecture, which is how do we make sense of this squiggly graph? We look at it and we just see a whole bunch of peaks. We see a whole bunch of lines. We see some numbers. What does this all mean? Well, we've already explained what wave number means. It means strength of the bond. We've already explained what the y-axis means. It means the change in the dipole intensity. So we've talked about wave number, we've talked about intensity. Now let's talk about shape. There's different ways that we talk about the shape of these peaks, right? So I'm going to bring your attention first to this peak that is located between 3,500 and 3,300 right here. You will notice that this peak is kind of broad, right? You can describe this peak as broad. We say broad, or you can say wide. I apologize for my writing. I am using the mouse. So you can call this a broad peak compared to this one. How would you describe the shape of this peak right here? If this one is broad, this one could be what? And this is English, by the way.
Narrow.
Narrow, right? Narrow is good. Let's call that narrow. Is it blunt? Is it sharp? Is it spiky? How would you describe this?
It's spiky.
Spiky, right? I'm sure if this was real and I was about to touch it, it would probably be very sharp as well. Sharp. Even though there are some words that we use as standard, I want you guys for now just to practice describing what you see. Use your words, right? They don't have to be exactly the specific words. We'll focus on that later. But I want you guys to be able to look at a peak and tell me, oh, that is a strong intensity, broad peak, right? So this one could be also described as strong. This is a strong, broad peak between 3,300 and 3,500 wave numbers. This is a narrow, spiky, sharp, maybe not as strong. We can call that medium. Narrow, spiky, sharp, medium peak at about 1,500. You see? This is how we talk about these peaks. When we're talking about peaks, we're using descriptor words. Is it broad? Is it narrow? Is it strong intensity? Is it weak intensity? Is it medium intensity? Is it very strong intensity? Is it medium strong? Is it medium weak? All of these words are valid, right? Because it's English. We speak English. We are looking at it and describing the properties of these shapes. So I want you guys to practice doing that. But notice how whenever I am describing these things, I'm giving you all of these three informations. It is a strong intensity, broad wave number, broad peak, right? We're describing wave numbers, intensities, and shapes. Those three things is what we use to talk about the spectra. Any questions about this so far? Because this is the key right here. What we're going to be doing now is we're going to be looking at spectra, and we're going to talk about what functional groups have what sorts of peaks, so that when we look at this, we can identify what we call the representative peaks, right? Which ones tell us what is there. All righty. So let me clear my drawings, and let's go ahead and move on to the next slide here. All righty. So again, usually it goes from 400 to 4,000. And depending on the bond strength and the bond polarity, you're going to have different x-axis values. So you can see here, single bonds, it's a little bit cut off, I do apologize, but single bonds are usually found between 600 and 1400. Not always completely true. I would rather say 90% of single bonds are found between 600 and 1400. This is where I want to make a very clear distinction, because depending on your professors, if you take other professors at other schools or if you speak to other chemists in other places, everybody has a different definition of what constitutes the fingerprint region. This means that these peaks are not necessarily the first peaks we look at. This is kind of the last place we look. We read the spectra from left to right. So I'm starting on the right side because I want to give you guys right away the emphasis. I was taught by my professor from Yale that the fingerprint region was from 1,000 and below. And then when I was at UCLA, everybody's talked about the fingerprint region as being from 1,200 and below. And then in this PowerPoint presentation, they talk about the fingerprint region being at 1,400 and below. I don't really know which one is exactly the right one. I have always considered 1,000 and below to be fingerprint region, so that's what I operate on. There are some peaks that will help you tell you which ones you have that are above 1,000 and below 1,400. So I don't really agree that those regions should be considered fingerprints. But if your professor from your lecture tells you this, stick to what they tell you. They are the ones that are going to give you the exam. They are the ones that are going to grade your work. So whatever your lecture professor tells you, stick to that. I'm simply telling you that there is no actual consensus between what is what. But you can clearly see, though, that usually the more right-handed lower number regions are called the fingerprint regions. Okay? Then we have the double bond region. Here we have our carbon-carbon double bonds, right? Double bonds are stronger than single bonds, so therefore their wave number should be bigger than single bonds. And sure enough, they're between 1600 and 1800, which is much bigger than 400 and 1400. So this is where you find your carbon-carbon double bonds. This is where you find your carbon-oxygen double bonds. This is where you find your carbon-nitrogen double bonds, so forth and so forth. These are going to be very iconic peaks, right? Like you cannot take organic chemistry and not tell me where the carbon double bond oxygen, we call that a carbonyl. You can't take organic chemistry and not walk away telling me where the carbonyl is found, right? I'm sure you guys have heard the phrase, the mitochondria is the powerhouse of the cell. Well, in organic chemistry, the carbonyl is always found between 1700 and 1800, right? You need to know that for sure. And then a little bit more in the 2000s, in the low 2000s, we have our triple bonds, carbon-carbon triple bond, carbon-nitrogen triple bond. Yes, we have a carbon-oxygen triple bond as well, and carbon monoxide. Any sort of triple bond is usually found over here. And again, you'll notice the wave number is larger because triple bonds are stronger than double bonds. And again, double bonds are stronger than single bonds. So you clearly see what I told you earlier, that the stronger the bond, the higher the wave number. And then finally, we have our polar bond region, right? We have between 2700 and 3600. We have our nitrogen hydrogen bonds, our oxygen hydrogen bonds, our carbon hydrogen bonds. This is where you're going to find those. And yes, they are single bonds. So why are they all the way over here? Because they're polar, and polar bonds are also strong. Okay, so it's about bond strength and it's about dipole change intensity, right? And polar bonds, even though they're single bonds, tend to be stronger than non-polar single bonds. But also, remember earlier when I showed you the water example, we had the stretching and we also have the bending. Stretching frequencies have a higher wave number than bending frequencies. So it also depends. You can have a carbon oxygen bending at lower wave numbers, and you can have a carbon oxygen stretching at higher wave numbers. So you also have to keep that in mind, right? Again, I don't expect you to know everything just from this one 5-minute overview, but just keep this in mind. This is something you're going to be thinking about for the next 2 weeks going into the final as well. All right. So this is kind of what we're looking for. The first thing is you kind of have to I would want to say memorize, right? I know a lot of professors are like, you don't have to memorize this. Why not? It's already in your head. You never have to refer to anything else again. Do memorize this, please. It will make your life easier. You should start by saying, okay, this is where the single bonds are, this is where the double bonds are, this is where the triple bonds are, this is where the polar bonds stretchings are located. And then once you know those regions, you can move on to the next step and your life will be much easier. So definitely, this is an important slide. I would definitely commit this to memory for sure. So any questions? All right. So let's start with the most simplest thing that we can think of. Just carbon hydrogens, right? Hydrocarbons, no oxygens, no nothing. Let's just start with carbon hydrogen molecules all by themselves. Have you guys started like nomenclature in your lecture? Like, have you guys started talking about how to name compounds like hexane, pentane, butane, propane? Like, are you guys familiar with this stuff?
Yes.
Yes? Okay. Sounds good. Yeah. So you should be using these terms. This is how we speak organic chemistry. Alkane is carbon-carbon single bond. Alkene is carbon-carbon double bond. Alkyne is carbon-carbon triple bond. And just like I told you earlier, stronger bonds have stronger wave numbers, right? Big energy, big wave number. Okay, so if you see down here, starting with the bottom left, you'll see an alkane, an sp3 hybridized carbon hydrogen stretch that is usually located around 3000. And this is where I need to make sure that you guys understand something very clearly. We are studying organic chemistry. So all organic compounds have carbon hydrogen bonds. So this signal is always going to be here. This signal is always going to be here at 3000 in some form. What does that mean? It's not necessarily the most useful signal, right? Of course, hydrocarbons have a carbon-hydrogen stretching. That's the definition of organic chemistry. But since sometimes those carbon-hydrogen bonds are double bonds, sometimes you will see a peak that's a little bit higher wave number than just 3000, right? So if you look at this middle example, you're going to see right here, you have your carbon-hydrogen medium sharp peak at about 3100. And that is because this is sp2 hybridized. sp2 means you have a carbon double bond somewhere. And so because it's a little bit of a stronger bond, it's going to take a little more energy to vibrate it. And that explains why the x-axis is a little bit more to the left. And likewise, if you have a carbon triple bonded with a hydrogen, your hybridization is going to be sp, and you're going to see this peak right over here. Again, kind of a medium sharp peak. And this is going to be located at around 3300 wave numbers, right? So triple bonds are stronger than double bonds. Double bonds are stronger than single bonds. So you should look for these things if you suspect that you might have an alkene or an alkyne, right? You never walk into these things blindly. You always have some idea of the product you're making. You always have some idea of what you're expecting in an organic chemistry lab, right? You cannot identify the entire molecule just from one spectra. That is insane. If you can do that, you should be developing theory at Harvard or at Oxford, right? Only a truly seasoned 20 plus year organic chemist who has done a lot of work could maybe guess the whole molecule based on the spectra. But this is just small pieces of the puzzle. You also use TLC, you also use NMR, you also use boiling points, melting points. These are all pieces of the puzzle, but you have to know what to look for, right? So in this case, you can see that as the hybridization becomes more S, right? The less p orbitals you have, the stronger your wave number is going to be. So therefore, sp3 is weaker than sp2, and it is weaker than sp. Or you can say it backwards. sp has a higher wave number, followed by sp2, followed by sp3. But they are all above 3000. And if you guys have ever seen those pictures of the caves, you always see that the caves have those peaks coming up from the top. Those are called stalactites or stalactites. I don't really know how exactly it's pronounced, but that's what I use to describe these. These are the stalactites that come out from the top. So every organic molecule has carbon-hydrogen bonds. So you are always going to see something at 3000 corresponding to your carbon-hydrogen stretching. Okay? Any questions about any of this? All righty. So again, this is just the first one, just pure carbon hydrogens, nothing else attached to it, just carbon hydrogens by itself. Alrighty. And by the way, these slides are posted in the module for Lab 4, so you can always go back and access these as well. Alrighty. Let's move on to the next one. Oh, we have an example. Okay, so here's octane. Octane is like octopus, 8 carbons connected to hydrogens, and it's all sp3. So again, if you look over here, at your, let me see, where is my drawings? If you look over here around 3000, you will see your iconic, stereotypical, always expected CH stretching located at 3000. And then over here, you have some bending. Remember, bending vibrations tend to have lower energy than stretching vibrations. All right. So always make sure that you know what it is you're looking for. And this is a simple molecule. There's nothing else attached to it. It's just this. All right. So this is just one example. Now we're starting to make some sense of these squiggly lines. All right. I think we have one more example. Yes, aromatic compounds, right? Are you guys familiar with this concept, aromaticity? Something that is aromatic. Have you guys heard that in lecture? Yes, no? I don't really know. I have someone in chat. It says, yes. Excellent. Thank you. Yes. So I think I'm muted. Sorry about that. I stayed muted. Aromatic means that we have a benzene ring. That is what the definition I am going to stick to for now. And the benzene ring has alternating single double bonds in the carbon. All of these are sp2 hybridized. sp2. And again, if you take higher division organic chemistry for your senior year, they're going to tell you that aromaticity means that the bonds are more stable. If the bond is more stable, it takes a lot more energy to vibrate it, right? And it's not really going to vibrate that much. So those peaks are going to be very weak, but they are still going to have a somewhat medium wave number. So you see over here, I'm going to use the color green. Usually we see these combination bands. They kind of look like the hills, the foothills on a mountain. If you see this on a spectra, you have good reason to believe you have some sort of aromatic ring somewhere. And also, notice how the peaks at 3000 that we expect every single time, notice how their intensity has changed. If we go back to the previous example, you'll see that they are very intense. They go almost to the bottom, to the x-axis. But notice here, the intensity has been reduced. Now they are medium sharp peaks because again, it takes a lot more energy to vibrate them, and therefore the dipole doesn't change that much, and that's why you see a reduced intensity, right? Aromatic rings are very stable. They don't really want to move. They want to just stay as they are. So when they do vibrate, they don't vibrate very much. And that's why you see all of these peaks are much sharper. Overall, your spectra is going to look much sharper. And you're also going to see very characteristic stretches. So again, another one to be on the lookout for is this one here. You have this sharp medium peak at around 1500. And this is where you got to be careful because a lot of people confuse a carbon-carbon double bond peak with a carbon double bond oxygen peak. They are close to each other, but one is at 1700 and this one is at 1500. So make sure you're always reading your x-axis before you begin any judgments. Okay? But this is just an example of how aromatic rings can sharpen the complete spectra and they have their own iconic representative peaks as well, right? And again, these are all carbon hydrogen compounds. So hydrocarbons, right? Nothing else attached to them. We can already get some information out of it. So any questions about any of this? Alrighty, moving on to the next slide. This is the cherry on the top. This is the whipped cream on the pie. This is the chocolate syrup on the mocha or the ice cream, right? Whatever you want to call it. The carbonyl. The carbonyl is part of so many functional groups. You need to know how to talk about it. You need to know what it means. So let me start by drawing it out. This word right here. You need to learn this word. You're learning how to speak organic chemistry. The carbonyl is the carbon double bond oxygen. You have to call it by its name, right? This is its name, carbonyl. I'm going to use this word. So when I say carbonyl, I'm talking about carbon double bond oxygen. Carbonyls make up many functional groups. So the carbonyl can be combined with a hydroxide to make a carboxylic acid. That's a functional group. The carbonyl can be by itself. That's called a ketone. The carbonyl can be combined with an oxygen carbon single bond. That's called an ester, right? You can see at the bottom, we have all of the names for the compound functional groups that contain carbonyls. Okay, so think about it like a first name and a last name, right? This is an aldehyde carbonyl. This is an ester carbonyl. This is a ketone carbonyl. Carbonyl is the last name and the first name is the functional group, right? So you need to learn what I mean and what your exam means and what your lecture professor says whenever we specifically talk about these types of carbonyls. But the word carbonyl by itself specifically means this right here, the carbon double bond oxygen. And this has a very characteristic region. You do need to remember, you do need to memorize this, right? Between 1600 and 1700, sometimes up to 1800, right? I want to say between 1650 and 1750 is usually where you find most of them. But there's always a few exceptions, right? This is chemistry. So depending on the type of carbonyl that you have, you're going to see that signal switch a little bit to the left or a little bit to the right. but they are always very strong intensity, very strong. We write that as VS like this, VS, very strong intensity. You need to know carbonyls, right? The mitochondria is the powerhouse of the cell. In organic chemistry, the carbonyl is between 1650 and 1750. Okay? Always. Always. You need to know this. Let me see. I think I have. There you go. So here is the family of the carbonyls. And if you don't know your functional groups yet, this is your sign to start memorizing them. Because if you're going to take OChem next semester, this is all they give you, right? You should know how to take the name of a compound and draw it based on the name. The name should translate to the structure. So we have an aldehyde, which is a carbonyl with a hydrogen. We have a ketone, which is just a carbonyl with two carbons around it. We have a carbonyl with an oxygen and a carbon. We call that an ester. We have a carbonyl with a hydroxide. We call that carboxylic acid. And we have a carbonyl with a nitrogen. We call that an amide. And we have other ones that, you guys can look up later. But each one has its generalized region. And I want to emphasize this is not absolutely 100% always the case. This is just guidance, right? Just like if you go to Mexico, you might have some tacos, but that doesn't tell you if you have al pastor tacos or carne asada tacos or cabeza tacos, right? There's many types of tacos, even though they all use tortillas. Well, there's many types of carbonyl functional groups, even though they all have carbonyls. And yeah, generally you can find them in these regions, but if you go to Tijuana, they'll like splatter it with a whole bunch of guacamole, right? Each one has its own little behavior, regional behavior. So yes, understand this, commit this to memory. Don't necessarily memorize it. Don't necessarily tell me, well, it's not at 1750, so it can't be a ketone. It could be. It could be. But now, if it's at 1500, yeah, definitely shouldn't be a carbonyl at all. So this is more of a guideline, okay? Like definitely understand it, know the general numbers, but this is not absolute. I just want to have that as a disclaimer. This is not 100% absolute. But you need to know the carbonyl. That's why I'm spending so much time on this. The carbonyl is the iconic functional group of organic chemistry. If you took organic chemistry and you can't tell someone what a carbonyl is, what were you doing in class, right? So definitely understand your carbonyls. Alrighty. So here is an example of two different carbonyl compounds. The top one is just a ketone. This one is just a typical carbonyl just by itself. It's just connected to two other carbons. And if you look here at 1718, you will see that we have a strong peak, strong, narrow peak, right? And if you look at this number here, it's probably 17-ish, 1710, 1705. But look at the shape. I want you to observe the shape. Actually take a look at it. This is a carbonyl peak. I always tell people, if you look at something, look for the carbonyl. If the carbonyl is there, you have significantly narrowed down what functional groups you might have in there. So this one is at 1718. You see the shape, very strong. It's almost touching the x-axis. Way stronger than the ones at 3000. Way stronger than the ones at 14 and 1200. Very strong peak. Look at the bottom one. This is an aldehyde carbonyl right here. Carbon, double bond, oxygen, hydrogen, right? Aldehyde. Look at the shape. It's almost very similar to the top shape. This one is at 1720. So again, it's between 1650 and 1750. And the shape is iconic. You can't really confuse it with anything else, right? Again, some people confuse it with the carbon-carbon double bond, but that is at 1500. That would be located right here. And it would be very sharp, very, very sharp. And it would be medium. So you cannot confuse the carbonyl really with anything else. It's so iconic. It's like this should be the first thing that either is there or isn't there when you're looking at these two. And also, in terms of your aldehyde, we do have a very special type of stretching that occurs as a result of this carbon hydrogen right over here. If you look between these numbers, between 27 and 29, you usually see some medium peaks that are used to identify an aldehyde, the carbon hydrogen of the carbonyl. So if you have these two spectra and you're comparing it, you can usually tell me which one is a ketone and which one is an aldehyde based on these peaks here at 27 and 28. And again, this is a general region. That doesn't mean they're always going to be exactly at those numbers, right? This is a guideline. So there's always a little additional clues that we look for to help us identify things, but we always start out by looking at 1700. Is there a carbonyl? Yes or no? If yes, what type of carbonyl is it? If no, move on to another functional group, right? You have already told me there's no carbonyls. So are there any questions about carbonyls right now? And again, just want to emphasize here, these are all of the possible types of carbonyls we could be looking at. So if you don't know your functional groups yet, we're at the point of the semester where you really got to start learning your functional groups. So no questions? I can move on to the next one. Alrighty. So one of the things that pops up in chemistry, something you're going to start hearing about a lot, is something called conjugation. And this is another fancy word that we do have to learn what it means in organic chemistry right here. Conjugation. What does that mean? Conjugation means you have an alternating single bond, double bond. So here's a double bond followed by a single bond. Here's a double bond followed by a single bond. Here's a double bond followed by a single bond. This pattern of double bond, single bond, double bond, single bond, this is called conjugation. So make sure you understand that. When we talk about a conjugated system, we're saying this has double bond, single bond, double bond, single bond, double bond, single bond, right? And that double bond can be a carbonyl. So if you look at this example right here, you see you have a carbonyl followed by a single bond, followed by an alkene, carbon-carbon double bond. So you have single bond, double bond, single bond, double bond. And what does that do? Well, it has a resonance structure. And this resonance structure makes that double bond into a 1.5 bond, right? So if you were just to have a regular carbon double bond, let me see. This one here, carbon, carbon double bond. This has a bond order of 2. And if you have a single bond, this has a bond order of 1. But if you have a conjugated system where you have a double bond followed by a single bond followed by a double bond, this has a bond order of 1.5. So when you do your hybrid resonance structure, it gets delocalized. So it's like a stick of butter, right? It gets spread out around the whole molecule. And that spread makes the bond weaker. Remember, double bonds are stronger than single bonds. So if you have a 1.5 bond, it's going to be in between. It's going to be a little higher than a single bond, but it's going to be a little lower than a double bond. And so if you have a molecule and you see a carbon-carbon double bond peak and you see a carbonyl peak and you know it could be conjugated, it's not going to be exactly at 1700. It's going to be a little bit lower. And you can see down here in this example that a conjugated ketone, in other words, a ketone that has a double bond, single bond, double bond pattern, has a lower wave number than a regular ketone. Conjugation lowers the wave number because a conjugated system spreads out the electron density. And instead of it being just a double bond, that double bond blends with the single bond to make a 1.5 bond. So a conjugated system lowers the bond strength, so it lowers the wave number. Any questions so far? All righty. So moving on to the next concept. And notice how this is all still related to carbonyls, right? You can go on and on about carbonyls. I have a whole book that specifically talks about carbonyls and infrared spectroscopy. It's like this thick. So yeah, people spend their whole careers on this. And this is why we know everything that we know about it. All righty. Now let's talk about alcohols and phenols, right? An alcohol is also called a hydroxide. Alcohol is just O single bonded to H. And a phenol is a benzene ring that has an OH. So be careful. I see people use the two interchangeably. Not exactly. When you say the word phenol, you are telling me that this is connected to an aromatic ring. When you say the word alcohol or hydroxide, you're telling me that there is no ring. Okay, phenols are very specific, alcohols are very specific. Both of these could be called hydroxide. That is its actual name, hydroxide. There we go, hydroxide. And again, just like carbonyls, this is so characteristic. It's like you just know it when you see it. So look at this example at the bottom. And I showed you guys earlier. Look at this example here between 3200 and 3600. It's a very broad peak, very broad, very blunt. You can call it soft because it's not sharp, right? So it's very rounded, right? If you see this shape and the wave number is kind of broad, or I should just say broad in general, and because it's an oxygen hydrogen bond, it's polar and the intensity is going to be strong. If you see this shape, you should say, oh, yeah, that's definitely an OH right there. So just take a quick look at it, like take it in, just see it. You see the shape of the peak, it's very broad. You see the intensity is strong in general. And you see that it covers a large range of wave numbers. This is a hydroxide peak. This is an OH peak. Very broad, large peak is what the slide uses. And so why do we have that range of wave numbers? Why is everything else much sharper, more spiky? Because remember, OH can form hydrogen bonds. And so not only are you vibrating the OH bond directly, you're also vibrating that very not so strong hydrogen bond. And so you have a range of wave numbers that represents a range of energies, a range of vibrations. And that's why you see this very broad peak, because you have a range of energies due to the hydrogen bonding. And so this again is iconic. You see this and you can't, like, you recognize it right away, right? So this is the example for hexanol. You can see you have your iconic OH stretch between 3200 and 3600, plus minus a few here and there. And likewise, not only do you have this oxygen hydrogen bond, you also have this carbon that is usually attached to it. So this carbon oxygen single bond is also polar, but this cannot form hydrogen bonds. And this is going to be at a much lower wave number. So these, we call these ether bonds, ether or methoxy or alkoxide. There's many different ways to call these things. These are usually found at around 1100. So you can see here we have this carbon oxygen single bond at 1100 wave numbers right there. So we'll see this again in a bit. But if you suspect you have an OH, a hydroxide, you should also be looking between 1100 and 1200 for this medium sharp carbon oxygen stretch. It's not as high of a wave number as an OH because it's not very polar. And it is a single bond, and there is no hydrogen bonding. So that is why you see it there. But usually you will see them in conjunction with each other. All right? So any questions about any of this so far? All righty. Okay. So let's see. I think this is another example. Oh, yes, yes, yes. So now we're starting to do compound functional groups. So carboxylic acids, again, you got to be careful with your names because the name tells me the type of molecule that it is. If you use the wrong name, you're giving me the wrong compound, right? Carboxylic acids are made out of two functional groups. They are made of your carbonyl. So this is your carbonyl right here. Let me just spell it out real quick. Carbonyl. And this is your hydroxide right here. And you got to be careful because I have people who point to this signal and they tell me this is a carboxylic signal. That is wrong. That is wrong. You cannot just say carboxylic because then I'm going to ask you, what part of the carboxylic? Are you talking about your carbonyl or are you talking about your hydroxide? You can't just say carboxylic. Carboxylic is the whole thing. You have to tell me this is a carboxylic hydroxide or this is a carboxylic carbonyl. First name and last name. You can't just say carboxylic because I have no idea what you mean. You're just guessing. So yes, you have to be specific, right? You have to be OCD level specific. And so a carboxylic acid contains both of these. So you're going to see both of the signals. The first signal you're going to see, we already talked about it, is going to be your carbonyl signal at 1700 right here. You see? So this is your carbonyl from your carboxylic acid. And the second signal you're going to see is the very, very broad signal from your hydroxide in your carboxylic acid. And you'll notice based on the range, if you look back at the regular just hydroxide by itself, this range is about 400 to 500 wave numbers. If you look at your carboxylic hydroxide, it almost has a 1,000 wave number range. It's a very broad signal. There's so much hydrogen bonding going on here. So you can easily tell whether you have a carboxylic hydroxide or a regular hydroxide based on the breadth of the signal. So keep that in mind. If you see a very, very, very broad signal in a high wave number region, you probably have a carboxylic hydroxide, right? And usually this range is going to be about 1,000 wave numbers right here. Very iconic. And of course, you can confirm because the carboxylic acid contains the carbonyl. So if you have that very broad 1,000 wave number wide signal, and you also have your carbonyl signal at 1,700, you have a carboxylic acid, right? And that's all we pay attention to. Yes, there's all these peaks right here. There's all these peaks right here. That's cool. I'm sure that means something, but we're trying to find the functional group. And these two peaks by themselves tell me the functional groups. So this is also why IR is interesting. We don't always have to interpret every single peak. We're just looking for the characteristic representative peaks. So any questions about this concept here? Alrighty, moving on to the next group. Ethers. An ether is a carbon double bond, I'm sorry, carbon single bond oxygen carbon bridge. So you have carbon something, and they are connected to an oxygen, the bridging oxygen. We call this ether. So if you have an ether, well, you have a polar bond. The polarity is going to go in the direction of the oxygen, just like this. And that change in that dipole is going to be visible, right? So again, usually you find this, since it's a single bond and the polarity is being shared by other carbons, it's going to be intense, but it's not going to be very strong wave number wise. And so sure enough, you find that here between 1,000 and 1,200. And usually this is more of like a confirmation kind of peak. Remember that if you have carbon and an OH, this carbon oxygen bond is also going to show up here in the same region. And if you have an ester, which we will talk about eventually, which is a carbonyl with a carbon single bond oxygen, you're also going to find that ester carbon oxygen stretch in the same region. So this gives you some information, but sometimes it's not enough to determine for sure which one you have. You usually compound it with other stuff. In this example, dibutyl ether, you can see the formula right here. You just have carbon hydrogen chains bridged by an oxygen. Remember I told you guys, what is this right here at 3,000? What are these? Stalactites, right? This is your carbon hydrogen stretches. This is everywhere. Every organic compound has them. Sometimes they don't tell you anything other than your compound is organic. So you cannot simply point to this and say, yeah, this definitely helps me. Everything has it, man. You know, we all have a head and a face and two eyes and a nose and a mouth. That doesn't mean that I can tell who you are, or I can tell your name, or I can tell where you're from, right? Every compound has them. It's just part of organic chemistry. So in this case, we would ignore these in the orange and we would only pay attention to this one to help us determine what functional groups are present in our molecule. Does that make sense? So any questions about anything so far? Again, and you might ask me, well, what about these right here? What about these? I don't know. Probably some carbon oxygen bends happening somewhere. We don't know. We just look for one or two characteristic peaks. That's usually all we need. And we usually don't go in blindly. We kind of know what we're expecting, or we have at least a set of molecules to choose from. So any questions so far? All right, moving on to the next one. Okay, so again, this is just another example, right? One of the other compound, one of the other compound functional groups that we have is a carbonyl with an ether. So carbon double bond oxygen combined with a carbon oxygen ether single bond. This is called an ester. Here we go. Ester. And the ester, well, we have a carbonyl, so we look at 1700, and sure enough, we see our carbonyl peak right here. Very strong, very broad at 1700, iconic. You cannot miss it. And we also have this carbon oxygen single bond attached to it right here. And remember, this is going to show up between 1000 and 1200. And that one is right here. And sometimes we see another type of bend. It could be asymmetric or asymmetric bend. I don't really know, but because we know that it's a polar bond, usually the strongest in the region is going to correspond to your carbon oxygen ether bond. But you got to be careful because an ether plus a carboxylic acid is an ester. So you got to call it by the whole name, right? If I ask you, what functional group is this? And you say carbonyl, you're only half right. So you're only going to get the half point. If you say ether, you're only half right. So you're only going to get the half point. You have to say ester because that's what it is. That is its name, right? I can't just point to a Toyota Tacoma and I ask you, what is that? And you say car. Yeah. What kind of car? Truck. Okay, but what kind? There's Fords, there's Toyotas, there's Hondas, there's Cybertrucks, right? You have to be specific. You have to be specific in chemistry. You can't just be general about these things, right? This is science. And then look at the bottom one. Here we have an aromatic ether. Let me use another color down in the bottom spectrum. I'm going to use pink. So right here, we have our molecule. And you see here, we have our functional group. So again, we have the carbonyl. And you can see right here, this carbonyl. It is conjugated because we have a double bond, single bond, double bond, single bond, double bond, single bond in the aromatic ring. So this one is still going to be a little bit less than 1700. And we also have this carbon oxygen single bond. So we look for the strongest signal between 11 and 12. And we see two of them. We see this one and we see this one. And whoever interpreted the spectra decided that both of them were going to be the carbon oxygen stretch. Remember, these are general regions, general guidelines. They're not always absolute 100%. That's why IR works. IR gives you a fingerprint of the molecule. We can identify what it is. Sometimes they all behave similarly, just like you can have loops, you can have whorls, you can have double loops in your fingerprints, but it's still a unique spectra. So just know the general principles, know the general regions. Sometimes there are going to be variations. Okay. And again, what about the rest? Well, here in the green, well, I already used green. Let me use another color. Here in the light blue, again, we have our CH stretches at 3000. Yay, we have an organic molecule. It doesn't really tell us anything. What about here? Well, notice how these are sharper. That's part of this ring right here. Remember, aromatic rings usually make the spectrum much sharper. And you will also look for some foothills up here. And so these foothills tell you, along with the sharpness, that this is most likely an aromatic compound. And what does aromatic mean? It means there is a benzene ring for now. Okay? And you might say, well, what about this one over here what about this one in the yellow, somewhere here at 700? Quién sabe, bro? I have no idea. That is definitely the fingerprint region. We don't look at the fingerprint region unless we have absolutely nothing else to go off of. Here we have the carbonyl and we have the carbon oxygen stretch. Therefore, that's all we need. This yellow, I'm sure it's something, but for now, we can't identify it, right? We don't really know. Any questions about this so far? All righty. So moving forward, amines. Amines. The amine, I'm sure you guys have heard of the singer slash rapper Aminé. That's not how we say it here. We say amine. Okay? You know what I mean? It's amine. NH2 or NH. If there is N and C and C And C, this is called amide with a D. Okay, so do not call an amine an amide. They are not the same thing. Amines have hydrogens, amides do not, but they both have nitrogens. Okay, so when I'm talking about amines, I'm specifically talking about nitrogen hydrogen bond stretches. And you can see two examples. Nitrogen hydrogen is polar, so it's going to be found at around 3000 to 3300. And this is what's really cool about it. Depending on how many nitrogen hydrogens you have, so for example, for hexylamine, you can see here in the middle one, you have two nitrogen hydrogen stretches. So therefore, you're going to have two peaks. You're going to have one right here, and you're going to have two right here. And you can see there's one and there's two. And if you only have one nitrogen hydrogen peak, you're only going to have this one, right? So this is one nitrogen hydrogen, this is one peak. And this is very useful because you can tell me whether this is a primary amine, NH2, or a secondary amine, NH. If you have no hydrogens, you're not going to see anything here at all. You're going to see that much lower in a lower wave number. That is your amide carbon nitrogen stretch. So make sure you understand the difference between amine and amide. The amide has the D in the name and it has no hydrogens in the structure. It's just carbon, nitrogen, carbon, nitrogen, carbon, nitrogen. Amines have hydrogens in them. So do not call an amine an amide and always look between 3200 and 3500 for those signals. If they are missing, and from the formula, you know you have a nitrogen in there somewhere, it must be an amide, right? This is where if you play Sudoku, you kind of have a better advantage. You're like, well, I don't have this number, I don't have this number, it must be the other numbers. Yeah. If you don't have peaks representing amines between 32 and 3500, you must have an amide. And then you look for something else. And also, amides contain carbonyls. So you would look for that carbonyl peak if you think so. All right. But these are also very iconic. This is very useful. You can't really miss it. And if you're suspecting you have an amine, you go to this region and you look for how many peaks you have for your amines. Okay? Any questions about amines? This is really all there is to it for amines. All right. So moving on. Now I'm going to see if you guys can kind of put this stuff together, right? Again, I don't expect you to be experts 100%. We just learned this stuff, but you're going to have the rest of this week and the rest of next week to study. What I would recommend before we move on to these right here, what I would recommend, let me stop sharing my screen real quick, is go to this website. I'm going to show you another really cool, useful website. Alrighty. So if you go on Google, you can go and type in Organic Chemistry Spectral Database, right? Organic Chemistry Spectral Database. And you're going to see this website pop up, AIST. And if you're taking 223B, you can still use this website next semester. My professor was the one that showed me this, and he would take examples that he uses on exams, and the examples that we're showing you right now, these all come from this website. This is the source. So remember it, bookmark it, use it. Use it to practice, use it to quiz yourself, use it to confirm, right? In science, we have the literature, we have the references. We can make claims, but we have to refer to something that validates our claim. So this is a good academic accepted source for any future work that you might do in organic chemistry. AIST, the spectral database for organic compounds. So you're going to go ahead and click on it, and you'll get to this website. Go ahead and put I agree. And then here you can see the menu. You can type in the compound name. You can type in the formula. You can type in the molar mass. If you know the CAS number, if you know the SDBS number, I don't really know what that means, to be honest. And then next semester, you're going to be studying hydrogen NMR. You can use this from next semester to practice. But for this semester, we're only going to be looking for IR. And then if you do decide to major in chemistry or forensics or biochemistry, you might also use it for future spectroscopic methods. So this is a very useful website. I highly recommend that you just remember it, especially if you're going to stay in science. So let me give you an example. I'm going to type in here acetone, and I'm going to click search. And you're going to see all of these results show up. Under where it says IR, Click yes. If it says yes, the spectrum is available. If it says no, you're out of luck. Alrighty, so I'm going to click yes in the acetone spectrum and look at that. You can see it right here. And so look at this acetone spectrum right here. Let me go ahead and do annotations. You see we have this carbonyl, right? Carbon double bond oxygen. Well, here's 1500, here's 1600, here's 1700, and look at that. This peak right here is our carbon double bond oxygen peak right there. You see that? And this is a real spectra that a real scientist took with a real instrument and published so we can look at it, so we can refer to it, right? So you can see the carbonyl peak perfectly corresponds to that carbonyl structure, right? And again, what's this over here? What's this at 3000? Do you guys remember? What's usually at 3000? It's present in all molecules. What is this stretch right here? You can type it in the chat, you can say it. What is that peak at 3000? It's everywhere. Every organic molecule has it. Carbon what? You got to know these things, guys. And you can guess. We're here to learn, remember? I got someone in the chat. H, that's right. Good, good. This is your carbon hydrogen stretch right here. Every organic compound is going to have something in the 3000 region because every organic compound contains carbon hydrogen bonds, right? So you can see how what we've learned can actually be used to look at the spectra, right? And again, you're going to ask me, well, what's this over here? What's this over here? I'm sure it's something, but if we just want to confirm that we have acetone and acetone has a carbonyl, if you're trying to make acetone and you don't see a carbonyl, something's wrong, right? Something's wrong. So it's not an absolute definitive method to confirm everything 100%, but it is a good way to see if you're on the right path. So again, use this website for your practice. Type in the name of your medicines, right? Acetaminophen, ibuprofen, so forth and so forth. And then see how the structure and the functional groups show up here. So let's do one more, and then we'll go ahead and do more practice. So let me go back. Let's type in acetaminophen. There you go, acetaminophen. All right, there you go. It has a different compound name. That is the IUPAC name, but it is acetaminophen. You can go ahead and click yes on the IR spectrum. And here's that spectra, right? So look, the first thing I notice, we look at the structure first, okay? Always look at the structure if you have it. So let's look at the structure. Here it is in red. We have this aromatic ring right here. Since we have an aromatic ring, the whole spectra should be a little sharper. And you can see there's a lot of sharp peaks, right? So that's already some confirmation. Since we have an aromatic ring, we should have a small pattern of foothills at around 17, 1800. And you can see right here, we call these overbands. That is the proper term. Overbands. No, that's supposed to be a B. These overbands are usually the result of that aromatic ring. So if you see the overbands and the whole spectra looks a little sharp and your structure shows an aromatic ring, you can definitely say, yeah, this is for sure aromatic. And more specifically, the carbon-carbon double bond for the aromatic shows up at around 1500. So that would be most likely this one right here, probably this one right here, probably this one right here. Which of the three? As long as you pick one and you're in the region, you have a pretty good shot of being correct, right? I don't actually know. I'll be honest with you. I don't actually know which of the three it is, but I do know that it's between those regions. So I do know that it should be there. Now, some of you are going to make a small mistake and you're going to tell me this one right here is also a carbon-carbon double bond, but that's not true. Which one is this one right here? Can somebody tell me? And look at your structure, right? And I'll give you a clue. This is 1700 right here, and this is 1600 right here, and you have a conjugated system. And it's also a very strong peak. So which one is this one right here in the green? You can type it in the chat or you can say it. It's the iconic one. It's the one that you cannot not know if you take organic chemistry. Look at your structure. Starts with the C. All right, we have an answer in the chat. Carbonyl. Excellent. Excellent. This is your carbonyl peak. Carbon, double bond, oxygen. And where is that? That is right here, you see? It's part of your structure. Acetaminophen contains a carbonyl. And you'll see that we have NHC double bond O. This is an amide group, right? Amide group, right? The whole group is called amide, but this specific part in the pink right here, that is your amine stretch. And that is most likely this peak right here. This one right here is most likely your nitrogen-hydrogen stretch. And since you only have one nitrogen-hydrogen bond, you should only see one nitrogen-hydrogen peak. All right? And then we also have a phenol hydroxide. I'm going to use, let's see, what color haven't I used yet? Blue. So this OH right here, well, hydroxides usually make broad peaks, right? So even though we don't specifically see which of the peaks it is, we can definitely say that the broadness of this is caused by your OH peak. So which of the two is it? Well, it could also have blended with the other peaks. But the fact that it's broad in general and that it's part of the structure means that you can claim that this broad compound peak is your OH peak. And then remember, all organic compounds have carbon hydrogen peaks. So if you look at 3000, you will see very weak carbon hydrogen stretches. These are your carbon hydrogen stretches. And they're part of an aromatic ring, so they're not going to be very strong at all, right? Aromatic rings are stable, so they're very strong. It's very hard to vibrate them. You're not going to see a very intense peak for your carbon hydrogen peaks. So again, I don't expect you to know how to do this right now, right off the bat, but this is how we put everything that we've gone over together, and we can use the structure and we can use the spectra to confirm whether we made the right compound or not, right? If you were expecting a carbonyl in acetaminophen and you don't see it, you messed up. You got to go back and make it again. Otherwise, when you sell it to the public, you're going to be lying and they're going to sue you and the company's going to get shut down. And this is how chemical mistakes are made, right? So again, this is real stuff. If you work in a pharmaceutical lab, you will be using IR for sure, right? So what about the rest of the peaks? As long as you can give me the characteristic ones for now, the rest of the peaks are up for debate. So any questions about how we're using this so far? So your post-lab quiz is going to give you spectra, and I might give you the structure, and I might have you do exactly what I just did right now. I'm going to show you, hey, which one is the peak corresponding to these groups, and you have to tell me. Okay? You have to tell me which ones they are, and you have to describe them. You know, the strong, broad peak between 31 and 35 is the hydroxide. The very strong, sharp peak at 1650 is your carbonyl. The set of sharp peaks at 1500 is my carbon-carbon aromatic peaks, right? You have to talk like that. You have to be able to tell me those phrases for you to speak correctly when you're talking about IR. That is what we are hoping to teach you in this class. All righty. And again, this is the spectral database for organic compounds. So please use this. I am going to use this website to pull some spectra for the post-lab quiz in 2 weeks, right? So make sure you practice, make sure you give yourself problems. Go to your medicine cabinet and look at the name of the molecules and type them in here and see if you can identify what it is. All righty. So I'm going to go back to the PowerPoint slide real quick. Let me see. Give me 1 second. I got to share the screen again. All righty. Here we go. Okay, so I think I'm back to the PowerPoint slides. Yep, perfect. Alrighty. So let's go ahead and start where we were. Oh man. Okay, here we go. I should have put start from this slide. Okay, here we go. Alrighty, so first one. Again, we only look for the important peaks. The first thing we notice is there is this very broad peak that spans 1,000 wave numbers here. And then we notice a peak here at 1,700. So you guys tell me now, I'm going to stop talking. You tell me what functional group is present here for sure. Alrighty, and then just make sure that when you guys send the chat, you do send it to everybody so everybody can also see your answers, right? We're here to learn, so don't worry about getting it right or wrong. We're learning, right? I did get a message that said OH. That is correct, but what kind of OH, right? OH the hydroxide, but we also have a peak at 1,700, so this is a very specific functional group. When you combine that peak at 1,700 and the OH, you get what? Perfect. And again, just a reminder, make sure that you address the chat to everybody, right? But I got a response that says carbonyl and an OH. Perfect. Perfect, for sure. So this peak at 1,700 is a carbonyl, which is your carbon double bond oxygen, and you have OH. So what happens when you put a carbonyl and an OH together? What do you get? What is the name of the functional group? What is the name of this functional group? You have to call it by its actual name. Carboxylic acid. Yes, thank you, Abigail. Perfect. This is a carboxylic acid, right? The carboxylic acid has a carbonyl peak at around 1,700, and it has a very broad hydroxide slash alcohol peak that spans 1,000 wave numbers between 25 and 3,500. I call it the beard. Right? A lot of chemists, they like to call this shape the beard, the wizard's beard. If you've ever seen, Lord of the Rings or any movies with wizards, you usually see like the dude or the woman, and they usually have a beard. I don't know if the women have beards in the movies, but and then they have their wizard hat, right? So there's the wizard hat. And so the wizard's beard is what we call him. The wizard's beard is very iconic signal shape for the carboxylic acid hydroxide. So if you look at a structure and you see a wizard's beard that has a 1,000 wave number width, you most likely have a carboxylic acid. How do you confirm? Look for your carbonyl peak at 1,700. Okay. What about the rest of the signals? We don't know, bro. We genuinely don't know. All we know is we have a carboxylic acid, and that's good enough because we're going to do NMR and we're going to do MS and we're going to do other stuff, right? So this is enough for us to accept and move on to some other analysis method. All right? So good stuff. Let's move on to our next example. What about here? First thing you should look at is, let's look at 1,700. Here's 1,700. Do you guys see anything there at 1,700? Are there any peaks? It's a yes or no question. Right? No, that's right. Thank you. Yes, there are no peaks at 1,700. So what does this mean? There is no carbonyl. No carbonyl. We can already eliminate ketones, we can eliminate aldehydes, we can eliminate esters, we can eliminate all of these functional groups by an absence of a peak. So even though the peak's not there, you can still get some information out of it, right? There is no carbonyl. So we move on to the other ones. Okay. What about this one here? I'm going to use pink. We have a very broad, medium strong peak at around 3,400. It's broad, so that gives me a clue. What is there? Perfect. Yes, this is a standard, representative, stereotypical, iconic OH signal right here. OH. Since there is no carbonyl, it is not a carboxylic OH. It could it be an aromatic one? Well, perhaps. I mean, it is kind of sharp, right? It could be an aromatic, it could be a phenol. And again, just a reminder, phenols are hydroxides that are attached to an aromatic ring. So this would be a phenol specifically, right? So if you suspect you have a phenol, what other functional group would you also look for? You have this right here that you would look for, right? That is a carbon-carbon double bond. Carbon-carbon double bonds are usually found at around 1500. And since it would be a phenol, it's most likely going to be sharp. So let's go to 1500. Do we see any sharp medium strength peaks that could symbolize a carbon-carbon double bond? It's a yes or no question. Are there any peaks there? You guys can see the spectra, right? Because I drew an arrow pointing to it. So either there is a peak where the arrow is or there isn't. That's right. The arrow is pointing straight to the peak. So since there is a sharp peak at 1700, and it looks like we have a slight overband, I'm going to say with about 80% confidence that this is probably a phenol and this is probably an aromatic ring, and that can be confirmed by this carbon-carbon double bond sharp peak at 1500. Okay. Do I know for sure? No. How would I confirm? I would do more analysis. I would read the bottle where I got it from. I would, if I'm trying to synthesize something that has a carbon-carbon double bond, I would expect to see the signal there, right? But I have suspicions and they're 80% confident regarding the carbon-carbon double bond. There is supporting evidence. That's the important part. There is supporting evidence. So I can make those claims, right? The only thing that would contradict that is the intensity of this peak here in the green at 3000. What is this peak here at 3000? It's everywhere. What is that peak right there? Every compound has them, remember? CH. Yes, that's right. Emily, CH. This is your CH stretching. Every compound has them. Sometimes it will be useful. Sometimes it will not be useful, right? Sometimes you do have to pay attention to it. Sometimes you ignore it. The key is if you only see that stalactite at the 3000s and you see nothing else, you probably only have an alkane or an alkene or an alkyne, right? But if you see that with other stuff, we kind of ignore it because the other stuff tends to be a little more important. Of course, you have carbon hydrogen stretches. You're in organic chemistry. You're looking at organic compounds. Of course, this signal is going to be there, right? Sometimes it's useful. Sometimes it's not. It depends. But you still have to know what it is. You still have to know where it's at. Okay. So excellent. Yeah, good stuff. All righty. Let's try the next one. What about here? So I just told you we can probably ignore these here because it's at 3,000. This is most likely our carbon hydrogen stretches, right? They don't really tell us anything. Yay, we have an organic compound. Awesome. What can we tell for sure? There's a signal here that has two peaks. What is that? Well, if you don't know, maybe you can ask what it isn't, right? If this was an OH, would you see those both of those peaks? If this was an OH, you would see something that is very strong and someone broad between 32 and 33, just like we did in our previous examples, right? Very iconic OH stretch. Since we do not see it, it cannot be an OH. So what else is polar that is similar electronegativity that can give you both of those peaks? What else could it be? And again, this is all you. You guys have to tell me. Alrighty, and Mia said amine. That's right. What kind of amine? Is it an NH or an NH2? NH2. And you know that it is an NH2 because you see two peaks. Each peak is an NH stretch. Perfect. Exactly. So this is NH, this is NH, and since we have two NHs, it must be NH2, an amine. All right. Can we tell anything else from here? There's some peaks here at the 1500s, but we don't really know what those are, right? Kind of hard to say. So the only definitive thing that we can point to is the NH2 peaks. And sometimes in IR, that's all you need. You just need one characteristic peak and you can ignore the rest for now. Make sense? So again, hopefully when you look at a spectra, you don't just kind of freak out and say, oh God, all these squiggly lines. No, no, no. Sometimes we just got to look at one set of squiggly lines. Sometimes we look at two sets of squiggly lines. They mean something. And once we have that functional group, remember the purpose of IR is to identify functional groups. Sometimes that's all we need. It can be that simple. All righty. Good stuff. Good stuff. All righty. So let's move on to the next example here. What about this one? Oh, this one has one peak. Look at the one that we just did and look at this one. You see? So what must this be? If it looks similar regions, but now we only see one peak. What is this one here? That is correct. Yes, this is an NH peak right here. There's only one peak. It's not very strong. Remember, the strength, the y-axis has to do with polarity, right? And nitrogen, it is electronegative, but not as much as oxygen. So again, if you're not exactly sure, if you're still confusing it with the OH, just remember that the OH peak is usually going to be more intense and it's usually going to be more smooth. So if this was OH, it would look like this because that OH has a bigger dipole change, it would be way more intense on the y-axis. NH, it has a dipole change, not as intense, So that's why the signal strength is not that strong, right? The intensity is not as strong. And since you only see one, it must be an NH peak for sure, right? This is your single NH peak right there. Make sense? What else can we determine? Is there anything at 1700? Nope, right? You can see over here, I'm going to use the color pink. You can see here at 1700, there is nothing, right? So there's no carbonyl, so it's not an amide. I don't really see anything else. What's this here at 3000s? This is everywhere, remember? You got to know when to talk about it and when not to. So what are these? We've talked about them pretty much every single time. What are these? They're everywhere. Every compound has them. The H. Perfect. These are your CH stretches right here. Oh, I don't know why I changed color. Hold on. I should be using pink. There you go. CH right here. This is always there. This is always there. So sometimes it's useful, sometimes it's not. All we know is that there is an NH peak right here. Make sense? Alrighty. Okay, let's see. I think we have a few more practice problems. Not exactly sure. Oh, okay. So again, look at the one before and look at this one so you can see the difference between the two. I think the shape and the breadth should be enough to tell you right away what this is. So which is this one? What is this peak right here? It's smooth, it's broad, it's strong intensity. What is this one? OH, exactly. This is your OH peak right here. And again, if you're not exactly sure if it's a carboxylic OH or a regular OH, just look at the width. I was gonna say breadth, but like width. Yeah, the width. This is between 31 and 35. So this only has a wave number width of about 300 wave numbers. If this was a carboxylic OH, it would be 1000. It would be much, much broader. And it doesn't look like a wizard's beard, right? There's no scruffiness at the bottom. So the fact that it's very smooth and it is between 32 and 35 and it's broad and it's strong intensity tells you right away this is an OH peak. And again, let's look at 1700. Is this part of a carbonyl? Let's see. I don't know. 15, 16. Here's 17 right here. Do we see any peaks at 1700? Are there any peaks here? The yes or no question. Either there are peaks or there aren't. That's right. No peaks at 1700. If there was a carbonyl, it would look like this. Something like that. Very strong peak. It is not there. There are no carbonyls. No carbonyls. And therefore, it cannot be a carboxylic acid. It must just be strictly an OH, a regular hydroxide, a regular alcohol. I don't really see any overbands, and I don't really see very sharp peaks in general, so I don't think this is a phenol. I don't think it's part of a benzene ring. Well, yeah, I'm not very good at drawing with the mouse. I don't think this is part of the benzene ring hydroxide right here, right? No, because there's nothing here either, right? There's nothing here. So it must be just a regular old-fashioned OH. And that's all we can tell. The last thing that we can confirm based on the spectra, remember, if you have OH, you must also have a carbon-oxygen single bond between 1100 and 1200. And so I see this bond right here. There's nothing else in this region. I can just say very confidently, this is your carbon-oxygen single bond right there. Because the OH is carbon, oxygen, hydrogen, right? So this carbon-oxygen is this one over there at about 1100. Okay. So you'll list it. It is part of the analysis. Can we tell anything else? We cannot tell anything else, right? Are you guys kind of getting how we do this? Are you kind of seeing the thought process behind this? It's like a Sudoku game. It's like a process of elimination. Alrighty. I think there's a few more practice. Ooh, this one is nice. Yeah, this one's. What about this one? What do we see or do not see here? This one's a bit too simple in terms of lines. We don't see many lines. We don't see many signals, right? That's already one big hint. All right, so if you're stuck, again, sometimes we look for peaks, but sometimes the absence of peaks is also very telling. So again, let's start with what we know. Are there any peaks at 1700 that we can assign to carbonyls? Yes or no? Yes or no question. So you tell me. Alrighty, no. Are there any strong broad peaks between 32 and 35 that we can assign to OH? No, right? Are there any wizard's beards that are very wide that we could assign to a carboxylic acid? Well, the answer should be no, because we don't have carbonyls, right? But there's no giant wizard's beards, right? Are there any sharp peaks between 1500 and 1600? Well, we see this one. This could mean something, but we don't know, right? Kind of hard to tell. Let's see. We have our standard run-of-the-mill carbon hydrogen stretches. I don't really see much else. So this must be what kind of compound? There's no esters, no ethers, no carboxylics, no OHs, no NHs. What kind of compound is it then? Starts with an A. It has a K in it. Alkene? Oh, nice. Ooh. I like that you didn't say alkane. You specifically said alkene, which is good. Why did you say alkene? Yes. So Julian said that there is a peak above 3000. Excellent, excellent. Very good. Yes. So I'm going to use the color. I haven't used green, right? I'm going to use green. This peak right here, it's not very strong, but it is sharp and it is a little bit higher wave number than this usual 3000s, right? So what's stronger than a carbon hydrogen single bond? An alkene, a carbon hydrogen double bond. So this is a carbon double bonded to another carbon that has a hydrogen. This is your sp2CH stretch. Yes, you have to write it like this. And this peak combined with this peak right here, this is your carbon double bond carbon peak. These two peaks confirm that this is an alkene, not an alkane, alkene. And there is nothing else, just carbon double bond carbon hydrogen. So excellent, Julian. Very good, very good. Yeah, these are the subtle details, right? Sometimes we'll see this and we're like, oh man, there's nothing that I know. There's nothing that I'm seeing. That itself is a clue. There is nothing else. So at the very least, you know that it's a hydrocarbon. Then you have to look for, is it a CH? Is it an sp2CH? Is it an sp-CH? Or is it an sp3CH? And that peak tells you this is an alkene. And now that we know that there's an alkene, we can definitely go back to this peak at around 15, 16 and say, yeah, that is your carbon-carbon double bonded peak for sure. And yes, you'll notice it is a little bit above the 1500, not exactly at 1500. It's still below 1700. So some people might point to this and say, oh, this is a carbonyl. It cannot be a carbonyl even though it's close to 1700 because carbonyls are very strong. If it is not very strong, it is not a carbonyl, even if it is in the region, right? We look at the shape, we look at the wave number, and we look at the intensity. Okay, so it cannot be a carbonyl even if it is close to 1700. So yeah, you have to put everything together. Excellent. All right, so all we can say is that this is some sort of alkene hydrocarbon and nothing else. Okay, let's see. Here's another one. Right away, I can tell what this is, right? What does this contain? There is a strong peak at around 1700. What is that? Can't move on until I get an answer. Excelente. Yes, a carbonyl peak. If you see a strong peak at 1700, it is a carbonyl peak, right? But you said very strong. Yes, but this is still the strongest of them all, right? The thing about this is that you'll notice the baseline is not exactly at 100. It is at 90. If you look on the y-axis, the line starts at 90. So whoever did this should prepare their samples better. But in general, we look at the shapes, at the trends. If it's at 1700 and it is a sharp, strong signal, you can bet with at least 80+% confidence that that is a carbonyl. Okay, so yeah, don't be scared. In fact, go here first. Look for the carbonyls first, because that already either confirms or eliminates many possibilities. So step one, look for your carbonyl peaks at 1700, right? Remember, if you know the mitochondria is the powerhouse of the cell, if you take organic chemistry, you should know the carbonyl peak is a very strong peak at 1700. Okay, if you learn nothing else from this class for IR, at least learn that. Okay, alrighty. There's also this peak that I noticed. Similar intensity, a little bit lower. It is between 1100 and 1300. What is this most likely? This could be a carbon oxygen peak. And I say could because I'm not 100% certain. It is in the region and it is similar intensity as the carbonyl. So it could be there. So I could have an ester possibly. It could be an ester. I can't say for sure. And then also, I want to bring your attention to this, right? This is a subtle detail. I noticed that there's two peaks right here, these two peaks. And there was one slide that we talked about earlier where this is a special case for a carbonyl, right? This is where knowing your carbonyl functional groups is really useful. These two peaks are below 3000 but above 2800. So between 2800 and 3000, If you suspect you have a carbonyl and you see peaks in this region, you might have an aldehyde specifically, which looks like this, right? And if I have an aldehyde, and then I have a peak here with the CO, I could have an aldehyde ether. I could have something that looks like this. I'm going to draw it in pink. O, O, H, and this could be some sort of R, right? Based on these three signals, I can start putting together a functional group. Do I know for sure? I can't say. That's the thing. IR is not definitive. It never confirms exactly what you have. If I'm expecting something like this, then yeah, I can make those claims. If not, I can't really say this with certainty. I can say, well, there's a strong chance I have an aldehyde, but there's also a strong chance I have an ether, and an even slimmer chance that I have both. Do I know for sure? I need more information, right? But I do know that there is a carbonyl peak, and I do know that I have something suggesting aldehydes or something suggesting esters. That's all I can say scientifically. I am not making a claim for sure. The only claim I can make is there is a carbonyl. All right. And let's see. One more here. All righty. Again, pretty simple spectra. Do we see carbonyls? Yes or no? Anything at 1700? Either we do or we don't. No, exactly. Right? No carbonyls at 1700. Do we see any OHs, any broad, strong signals between 32 and 35? Any OHs perhaps? Again, it's either yes or no. Do we see something that looks maybe like this at 32 to 35? Do we see something that looks like this? Well, I'm drawing it, right? So no, that's right. No, we do not see it. Perfect, right? Do we see a carbon oxygen single bond at around 1100? Well, I'm drawing it, so obviously we don't see it, right? We don't really see much here. The only thing that we do know is this peak right here. This peak could be a carbon double bonded carbon because it is at 1500. And if we did see that, we could confirm by looking at around 3100 for something else. But I don't really see that there, right? As far as I know, this is just a regular boring alkane. This is just your old-fashioned standard alkane. What are these peaks here? I don't know. There could be some bending. There could be some sort of resonance going on. Maybe the solvent that it's in. Maybe there's some contamination in there as well. It really depends, right? Remember, at the end of the day, we are humans making these compounds, looking at these spectra. But does anything in particular stand out? Not really. So since there's nothing, all I can say is this is some sort of alkane. And also, we do have the usual expected CH stretches at around 30, around 3000. There you go. Sorry. Yeah. CH stretch, right? And again, don't get confused because you're gonna say, well, you just told me that this might be an aldehyde here. Right, but if you were expecting this to be an aldehyde, you should also see a corresponding carbonyl at 1700, and I don't see one. So even though it might look like an aldehyde, the fact that there's no carbonyl means it's not an aldehyde, right? If there's an aldehyde, you would see a carbonyl peak. So all we can make any claim about for sure is that this is just some sort of alkane. And sometimes that's just it. We need more information. All righty. Here's another one. We saw this one earlier, so you should already be more familiar with it. Which one's this one? Which one is this one more likely? There's two peaks. Not very strong, so not very polar. Still polar though. That's right. Abigail said NH2. Exactly. This is an NH2, and you can tell right away once you have enough practice. right? Again, here's your standard CH3s or your CH. There's no carbonyl at 1700, right? There is a peak here at roughly 1600, but it's not very strong. So we cannot call this a carbonyl. If this was a carbonyl, it would be much, much stronger. This would look all the way down. Remember, carbonyls almost touch or significantly are lower than 50%. So what is that there? I don't really know, man. So yeah, that's all we can say. Just NH2. We can't give any more information. We cannot assume any more information, right? And that's it, just like that. So, alrighty. Let's see. Are there any more practices? Oh, this one. Okay, this is a really bad spectra, right? Look at the baseline. The baseline here is at 50%. Whoever took the spectra needs way better training. But regardless, just like your TLC plates, sometimes they're not very aesthetic. We can still get information out of it. So, what is here? Step one, look for your carbonyls. Okay, here's 1700. Do we see anything at 1700? Even though it's a bad spectra, do we see something that we recognize? Mia says yes. So what is this peak right here? What is this called? The iconic peak. What is this peak here? You need to know it. Very iconic. First one we look for. Carbonyl. Thank you. This is a carbonyl peak for sure. Even though the resolution is not very good, the fact that it's at 1700 and it's strong, almost touching the axis, tells me this is a carbonyl. And I noticed this extremely wide, 1000 wave number wide signal. What is this one? Just based off of the width alone. So we have a carbonyl peak, so we must have a carbonyl functional group. What is a functional group that has a carbonyl and something that gives a very wide signal? OH, exactly. So we have an OH signal. OH in general gives very broad signals. Sometimes they're broad, but not too broad. Sometimes they're extremely broad if they are part of a compound functional group. And again, this spectra specifically is not very good, right? You're not always going to have perfect spectra, but you should still know the regions and what to expect. So we have OH and we have carbonyl. What is the name of this functional group? And we also saw it earlier. So again, you got to be able to tell me this on the quiz and you got to be able to tell me this on the final and next semester as well. What is this functional group called? Carboxylic acid. Yep. So you say, I have a carboxylic acid in my compound. Yep. All righty. All right. This is the table you're going to get on the final exam. So make sure you go back to these slides and you study it, right? Do you have to memorize it? It never hurts to memorize. It never hurts to memorize, right? Especially now where everything is easily accessible. The more you challenge your brain to remember information, the better off you will be. And then if the internet ever goes out for whatever reason, you still have the knowledge in your brain. So make sure you study this table. Make sure you use it to practice the examples. Make sure you go to the AIST database and look up stuff on your own and practice. And remember, these are guidelines. This is not 100% absolutely every single time. Okay? So I believe this completes our lecture for infrared spectroscopy. Are there any questions? Alrighty. Well, if there are, you can always come to office hours. You can ask me in the chat. This does complete our lecture for today, so thank you very much for your attention. And remember, in 2 weeks, we will have a post-lab quiz, and I will be asking you about these kinds of stuff. And your worksheet, your Lab 4 worksheet is also due in 2 weeks. It covers all of these topics, and this will show up on your final exam. So make sure that you do study. This is very important. Just because we're on Zoom does not make it any less important. So thank you guys for coming. I really appreciate it. And feel free to send me any emails or ask me during class or just come to office hours. I will stick around a few more minutes, but otherwise, this does conclude our lecture for today. And I will stop recording now. So thank you very much for being here. I do appreciate it.